Chemistry is beautiful. The endless variety of snowflakes, the astounding mechanics of our cells' megamolecules, the rainbow of fluorescent proteins. It is a work of art. It's also a long way from the usual view of chemistry, a world of oil spills, huge chemical plants, and endless, colourless solutions. But the beauty is there if you know where to look.
Drop of a colorless solution into another colorless solution turns brilliant pink. As a child, it's like magic, but you understand the magic.
The beauty of chemistry is in part in the shapes of the molecules and understanding the architecture of the molecules.
And one of them is hemoglobin. It's a fantastic molecule. If you watch this molecule, no one can be other than amazed if they see it for the first time.
In chemistry, this beauty doesn't come out of the mind of a great artist. It's inherent in nature. A large part of what chemists do is to try to unravel this beauty, to look at the mechanisms driving the endlessly complicated world around us. The beauty of chemistry is that if you can find out what is going on in one place and find a repeatable pattern, you can predict what will happen somewhere else. The beguilingly simple equations that chemists create to describe their observations often hold extraordinary power.
For the scientists, you can find beauty in equations, right? Beauty is a sort of cathartic response within you.
So let's start with the Schrödinger equation, which I consider to be gorgeous. I've read 2 or 3 of these papers that established the Schrödinger equation by Schrödinger, and I was almost blown away by it. He started from classical mechanics, and with really sort of a sleight of hand, it ended up in a page or 2 with the Schrödinger equation, which underpins everything about the electronic structure of molecules. It was just breathtaking. Got all of chemistry in half a line.
There's not only a beauty of simplicity, but often there's a kind of symmetry. And sometimes you can recognize that you're wrong because it doesn't feel right. It feels asymmetrical in some sense or another. I think that matches in beauty any of the common objects of beauty.
The equations that Schrödinger, Kern, Marcus, and hundreds of others developed describe the nuts and bolts of the world around us. It's like taking the back off that perfect Swiss watch and seeing the endless cogs whirl. For the scientist, the mechanism might be beautiful, even if the watch face isn't.
The periodic table for me is one of the most beautiful things around. It underpins the whole of chemistry for me. It's the coat hanger on which we hang our understanding of it. It explains, therefore, the whole of life as well.
Like an artist endlessly searching for beauty and truth in their work, the dream of finding that really beautiful idea is still what keeps scientists up late at night all around the world.
I wrote with my supervisor a paper and derived a certain equation. But it was messy, ugly, messy. And I found just by changing the order, everything became simple. It's just like popping out. A simple result came out. And that's the result that's used today. That was maybe the most exciting thing in my scientific life. It was really a eureka.
I've started writing this equation on napkins. I leave it in a restaurant. And my wife is worried that I'm going to become someone who puts things on walls. But yes, equations are beautiful.
Even when ideas are beautiful enough to transform scientists into graffiti artists and Nobel laureates, they're still just ideas. They exist in the realm of ancient Greek philosophers and their modern-day equivalent, theoretical physicists. Chemists deal in the real and the tangible. They need a way to test these elegant daydreams. In short, they need experiments. And to a chemist, there are ugly experiments, and there are most certainly beautiful experiments.
You have an idea, and it works, but it works better than you expected. Not only better than but in a totally unexpected way. And you realize that nature's a lot cleverer than you are.
Harry Kroto and Robert Curl were trying to look at the formation of matter in and around stars. Aided by a brilliant bit of apparatus designed by Richard Smalley, they not only produced but identified and purified a new sort of carbon.
We did this experiment to simulate the conditions in a star. You know, what use is that? I mean, what sort of use is that to chemistry? And then we discover this beautiful molecule C60, which is related to architecture.
They produced something that was just beautiful through and through. The experiment was beautifully simple but told you so much. The mathematical elegance of the structure spoke volumes. And yet the spheroid structure of C60 had a symmetry and beauty even the untutored eye could appreciate.
Chemistry is analogous, I think, to an impressionistic painting. An impressionistic painting is a marvelous thing, but you know, if you stand too close to an impressionistic painting, it's completely meaningless dabs of paint. If you stand too far away, it's equally meaningless blur. At the right distance, it's uncanny, it's fabulously, you wonder how the artist created this dabs of paint, what you see in it. And chemistry is exactly like that.